Hello, thank you for coming to this talk. Thanks to the COSPAR organizers for inviting me, and thank you very much for your creativity in organizing this meeting during a global pandemic. We appreciate it. My name is Andrea Lohman, and I'm talking to you today about nanohertz gravitational waves and space-based navigation using pulsars. And I will tell you what those have to do with each other. The short version, the punchline, is that they both have to do with this small refrigerator sized thing that we put on the International Space Station in 2017. It's called NICER, the Neutron Star Interior Composition Explorer, and it's an X-ray telescope that is looking exclusively at neutron stars. This work is done in collaboration with the Nanograph collaboration and with the NICER Precision Timing Working Group, many of whose names I'm standing in front of, sorry. And also the Haverford team. These are my students with whom I work, and also Natalia Lewandowska is an assistant professor there as well. Here's a gravitational wave experiment with which you are probably familiar. This is a picture of Virgo in Italy. In the interferometer way of detecting gravitational waves, you have a laser at this base station, and you split the laser into two pieces, and you send one piece down one arm and the other piece down the other arm, and they reflect off test masses at the end of the arms, come back to you, and you measure the difference in phase of the two lasers at the base station. And by that way, you detect any changes in the fabric of space-time, the curvature of space-time along the arms of your detector. The pulsar timing experiment is completely analogous. Here's what the pulsar timing experiment looks like. Instead of generating your pulses at Earth, you let the pulsars, these astronomical objects that pulse very regularly, give you the electromagnetic wave that you then receive at Earth, and you are looking for, again, phase differences in the arrival times of the pulses from the pulsars at Earth. There are several differences. One is that the arms are much longer. The arms are something like 1,000 parsecs long instead of being 3 or 4 kilometers long. Instead of having 2 pulsars, we actually have 40 to 50 pulsars in the pulsar timing array. I just pictured 2 of them here to make the analogy with LIGO and Virgo. And the gravitational waves to which we are sensitive are these massive black hole binaries that is in a cartoon here that I got from NASA. And you can see that the massive black holes are spiraling around each other, creating ripples in space-time. And those ripples in space-time are then influencing how long it takes the pulse to travel from the pulse to the Earth. The gravitational waves to which we are sensitive are in a different wavelength regime from LISA and LIGO. You're familiar, probably most familiar with the LIGO experiment because they've had such exciting results in the last couple of years. Right above my head here is the LIGO experiment. And they are sensitive to gravitational waves in hertz and kilohertz frequencies. And LISA, the laser interferometer space array, is sensitive to millihertz gravitational wave frequencies. And then the pulsar timing experiment is sensitive to nanohertz frequencies. These numbers are very small, sorry, but that's 10 to the minus 8th right here. So 10 to the minus 9 is here, and 1 over a year, I think of these more in periods than in frequencies, but 1 over a year is right here. And so you can see that the International Pulsar Timing Array is the one that's pictured here, is most sensitive to wavelengths of a year in gravitational waves. The vertical axis is characteristic strain, which is the amplitude of the gravitational wave. That's how we measure amplitudes of gravitational waves. And what characteristic strain refers to is the fractional change in length that a gravitational wave creates as it passes by. So if you imagine this pencil, pretend it's 10 centimeters long. If a gravitational wave comes through and changes its length by 1 centimeter as it comes through, then this characteristic strain, the strain that gravitational wave has is 1 centimeter divided by 10 centimeters. So that's a 0.1 strain of your gravitational wave. So that's a very big gravitational wave. These gravitational waves that LIGO has detected and that LISA and pulsar timing arrays are hoping to detect are much smaller. So these numbers are like 10 to the minus 24. LIGO detects things like 10 to the minus 22 in strain. Pulsar timing arrays need to detect something like 10 to the minus 15 in strain in order to detect gravitational waves. So this is sort of the landscape of gravitational wave detectors in existence and to come. And I wanted to point out that this plot was made on a web page called gwplotter.com. And you can go to that web page and choose which things you would like on this plot. I really like this web page. It was done by Chris Moore, Rob Cole, and Chris Berry, formerly of the Gravitational Wave Group at the Institute of Astronomy at the University of Cambridge. So just to give you a sense of what that means, what does that mean for what we can detect as a pulsar timing array, as a gravitational wave detector? I just did sort of the rough version of the quadrupole approximation to gravitational waves to figure out what the effect would be, excuse me, on pulsar timing. And the effect ends up being about 50 nanoseconds. So that's how late or early you would expect a pulse from a pulsar to be for a gravitational wave that was created by 2 billion solar mass black holes with a period of a year. So they're going around each other once a year, and they're at a distance of 100 megaparsecs. And you can see the way I wrote this formula, how to scale those numbers for other objects that you are interested in. So that's just a number to keep in mind, that those values, 2 billion solar mass black holes at a year, 100 megaparsec give you 50 nanoseconds. That's just a good number to keep in mind as we look at some data. So where do you get such massive black holes going around each other? Well, it turns out you expect that to happen often in the universe. Every time galaxies merge, we expect that there's a black hole in the center of each of them. And as they come together, those black holes will form a binary. And then that binary will produce lots of gravitational waves. And we actually expect a background of gravitational waves across the universe. So what have we found so far in the pulsar timing array? The Nanograv 12.5 year data release paper has just come out. It's on the archive. I gave you the archive address there. And what we have found is a common red noise process. So we can't say that this is gravitational waves. What we can say is that there seems to be a red noise process with an amplitude that's shown over here. I showed you the probability density. This is from that paper as a function of the amplitude. So the amplitude seems to be in between minus 14.5 and minus 15. So that's that 10 to the minus 14, 10 to the minus 15 that I was showing you on the previous plot of the spectrum that we expect. And so there is a red noise process. It was modeled as a power law with a spectral index of 13/3 or negative 13/3. It's a red process. And that's what we expect to get from the mergers of many supermassive black holes across the universe. So that's the background that I was talking about from many, many such supermassive black hole binaries. So again, that's not a detection, but it's one of the things that that common red noise process could be, is the gravitational wave background. There are other things that it could be, which brings me back to NICER, the X-ray telescope that's on the International Space Station. So for example, one of the sources of noise in the pulsar timing array data is the interstellar medium. So here's a cartoon made by Adi Pathastrati, and it shows the ionized hydrogen that is pervasive around the universe. Here's a cartoon of the pulsar, and the electromagnetic wave has to travel through the ionized hydrogen in order to get to the telescope here that's behind my head. And the interstellar medium will enact a delay on the pulsar signal. And that would be fine if it was a constant delay, but it's not a constant delay because the pulsar is moving with respect to this interstellar medium, and the interstellar medium is changing. But more importantly, the pulsar is moving with respect to that. So that's a source of noise that we, as radio astronomers, have to worry about and take out of our data. And Nanograv has done lots of work to remove those signals from our data, but that's one source of noise that we have to deal with. So what if you could have a data set, a pulsar timing data set that didn't have any of this ISM noise in here? Then what if you could remove that problem, that noise from your data set? That's what NICER does. So here's NICER. Here's the International Space Station. Here's the solar panels of the International Space Station. Here's the Neutron Star Interior Composition Explorer that is plugged in using power from the space station, so it doesn't have any consumables. So it's been up there for over 3 years now, 3.5 years. It was launched in June of 2017, and it is looking exclusively at pulsars. So the thing about looking in X-rays for pulsars, there are two things. One is you don't get very many photons because pulsars are notoriously dim in X-rays. So you give up some signal, but you also give up some noise, because this effect that I showed in this slide is dependent on the frequency of the electromagnetic waves that are going through the medium. And in fact, the delay is proportional to 1 over the frequency squared. So the relationship between the frequency of X-rays and the frequency of radio waves gives you a situation where basically the X-rays are not delayed at all by that interstellar medium. So you have a signal, you have an electromagnetic signal that is unaltered by the interstellar medium. That's what you get from X-rays. So what can you do with that? Well, one thing, what we have done so far is achieve our mission goals, which is to demonstrate that we can time 2 pulsars with timing accuracy of 1 part in 10 to the 14th using X-rays. So that was one of the mission goals of NICER, and we have achieved that with this paper written by Julia Denova that came out in 2019. So, mission accomplished. What else can you do? So then you can start to ask, well, what's the actual spectrum of the noise that you're getting from the pulsars? Because our data set is the first data set to not have any influence from the interstellar medium. The radio data sets, you can measure the spectrum of noise in the radio data sets, but you're always wondering what part of that spectrum is influenced by the interstellar medium. So if we can measure the spectrum of noise in these data, we'll actually be measuring the spectrum of either something intrinsic to the pulsar, which would be interesting because it's not known what noise is actually intrinsic to the pulsar. And second of all, we could be measuring gravitational waves without the influence of the interstellar medium. So this is the posterior from only 1 year of data, and my student Sergio Montano is working on this right now for his senior thesis. And so he's working on incorporating the 3 years of data that we now have from NICER. But this is the posterior on a plot of the amplitude and the spectral index. So we assume a power law for this noise, and you see how can you limit the posterior. So with 1 year of data, we're already placing limits on the amplitude of this noise source in the NICER data at something like 10 to the minus 12.5. Because you can see that there's no density, there's no probability density at amplitudes higher than that. So with more data, we'll be able to limit that more. And the other thing Sergio is doing, which I think is really cool, is asking the question, what should future X-ray missions do in order to actually make this detection of the amplitude and the spectral index of the noise in the pulsars? So he has a mind to think about strobacks and think, what is the cadence and the sensitivity that you need in order to actually make a detection of this spectrum. So watch for that paper, hopefully sometime in the next year. We're trying to get it out in the next couple months. and we hope that that study, that NICER is then sort of a pathfinder for future X-ray missions to continue this work and see if they can limit or detect the red noise in pulsar timing. Another thing you can do is space navigation. This was done by the Sextant team in NICER. And this has been published. There's multiple articles. I put one on here called the NASA Sextant Mission Operations Architecture, and you can see the list of authors here. It's an Acta Astronautica. But the idea here is that you've got some pulsars. They used 6 pulsars. And you have your spacecraft here. Here's a little cartoon of the International Space Station. And you can use the arrival times of those pulsars, as long as you're keeping track of the pulse number, to figure out where the spacecraft is in space. So, and this has been demonstrated now using NICER on the International Space Station, and they achieved a spatial accuracy of less than 10 kilometers. So this has been demonstrated now. It's very exciting. There's another way that you can do this. So this is great if you are anywhere in space. If you're out in space anywhere, you're flying to Alpha Centauri and you want to know where you are, you can use this method because it doesn't depend on you being close to the Earth, which is why it's so great, because all of our navigation methods now are currently referenced towards the Earth, but you don't need that in this method. There's another idea that was brought to me by Kent Wood, who I think many of you in this room know, and Nate Rule and Noah Schwab are 2 Haverford students that are working with us on that. And the idea is that when your spacecraft gets close to Alpha Centauri, for example, or the planets, more particularly one of the planets around Alpha Centauri, then you can use a horizon crossing method to figure out where you are. And that should be able to get better accuracy than the sextant method. And that's what we're working on, is how accurately can we get the position from a horizon crossing. So this is a cartoon that Nate and Noah drew. The idea is that this circle is the Earth, the inner circle is the Earth, the outer circle is the orbit of the spacecraft. And the red spots are 3 different positions of the spacecraft as it's going around its orbit. The S infinity stars over here are actually the same source. In our case, we actually observed V4641, which is a black hole that's currently in outburst. And this, so at these different positions, the signal is going through different amounts of atmosphere. And the different amounts of atmosphere that it's going through will reduce the flux that you're observing from the black hole. You can imagine if there was one more red spot here, right here, you don't see the black hole at all. And then as your spacecraft moves around, the black hole will come into view. So we have this observation. It's actually a little tricky to do on NICER, because NICER is, you have to figure out how to track the source before you can see the source, which is an interesting engineering problem. But here is the horizon crossing. So here's a picture of the flux increasing as the source comes into view at 4 different energies. And so here's 0 flux, and then as the source rises, then it comes into view. And the idea is, if we look back at this plot, that if you know what time this happened, and you know the location of this source that you're looking at, and we're thinking you need to know the pole of the orbit, but this is the sort of thing we're figuring out now, is what do you need to know ahead of time to actually figure out where you are in space? But certainly if you know the pole of your orbit, the location of the source, and the time that the horizon crossing happened, you should be able to figure out your position in space. So that's what Nate and Noah are working on right now. And yeah, we're hoping to get maybe 1 or 2 kilometer precision from that. That's what our rough estimates tell us. So in summary, pulsars make a galactic scale gravitational wave observatory, which is poised to detect gravitational waves in 5 to 10 years, although we may be seeing a hint of gravitational waves right now. The common red noise process could be gravitational waves. Individual and collections of supermassive black hole binaries with year-long periods are the dominant source in the band. The X-ray telescope NICER provides the first data set that's free of the influence of the interstellar medium, which is a major source of noise in the radio data. And so could possibly lend really interesting data on what the pulsar itself, what the intrinsic noise of the pulsar actually is, and or help us detect the gravitational waves that we're looking for using the pulsar timing method. And finally, there are at least 2 different ways that you can use an X-ray telescope like NICER to do space navigation. One is the method that Sextant has demonstrated, and the second is using the horizon crossing that Nate and Noah are working on. Thanks very much. Thanks for listening.